Yeah. Dr. Manoj, have you joined?
Yeah, I've joined.
Okay, can you just share your screen? We'll just see whether you're able to share. You're audible? Yeah.
Yeah, just give me a minute. I'm installing this WebEx app on my tablet.
Sure.
I'll share my screen in a while. Can you hear me?
Yeah, Dr. Manoj, your screen is visible. I will. Swarnima, please introduce the
Okay.
chief guest. Yeah, thanks for joining. Please, Swarnima, please introduce the chief guest.
Thank you.
Thank you, sir. Good afternoon,
Thank you.
everyone. Welcome to last day of the FDP. For the first session, we have Dr. Manas Goda, who has obtained his BTech degree from Bangalore University. He obtained his MTech in Signal Processing and Communication from IIT Kanpur in 2014. He has done his doctoral research on quantum communication at IIT Madras and graduated in 2021. Since 2021, he has been the quantum architecture scientist at Xanadu Technologies. He has numerous publications in top quality journals and patents to his credit. It is our distinct pleasure to welcome him to deliver today's lecture. Welcome, sir.
Thank you. Um,
You can
just give me a
proceed, sir.
minute. There's some problem with the speaker. Just can you hear me?
Yeah,
Yeah,
you're
yeah.
audible, sir.
Yeah, I think there is some echo. Hello.
There's some echo, I think.
Yeah, there is some echo.
I have muted all. You can again try talking. Yeah.
Okay. Is it better now? Can you hear
Yeah,
me?
it is better now. Yeah, yeah.
Okay. Thank you.
Yeah, yeah.
Okay. Thank you. Thanks, Darshan, for inviting me to give lecture here. So the topic of today is quantum computation. So we'll see how we can use quantum systems to make computation systems better. So our world, so the world around us is inherently classical, and we obtain information so majorly in two modes. Either as analog signals, where we have continuous stream of data, like temperature at a place, or the pressure at a place, or it can be digital information, as in, for instance, the data sent from your computers or mobiles. And this information is stored and processed digitally as this port has its own advantages. So the information unit is called a bit in case of classical computation, and it can take two values, either 0 or 1, or true or false, as you wish to call it, and it's a scalar quantity. So you can form, so you can take these bits and you can form a bit string such as this, which can denote classical information. So processing classical information typically means like you take multiple bit strings and form a function of them, and then you obtain some quantity here, which is so which can be either a bit or a string of bits. For instance, if you take the sum of all these bits, then y bar is a bit string. Or if you just take the sum of all the bits in this, then you have a single bit of information. So there are some shortcomings of classical computations. So classical computations, so they're an easy way to simulate processes in the classical way. For instance, we in electrical engineering committee do it left and right. For instance, in simulating communication systems, signal processing systems, and so on and so forth. But there are certain processes nature which cannot be simulated on quantum on classical computers. For instance, if you want to simulate a quantum system such as interaction of two molecules and so forth, so such processes cannot be simulated on a classical computer because those systems are inherently quantum and they have certain non-classical effects which cannot be accounted for by the classical computer. And there are some other classical processes which can take too long to solve on a classical computer. For instance, factoring two prime integers. So factoring integers into two prime numbers. So this is the backbone of AICTE system, and the strength of the AICTE system lies on the fact that it's hard to factor an integer into two primes. So we do have some limitations, inherent limitations when it comes to classical computations. So can we overcome these classical? So can we overcome these limitations by going to quantum systems with reasonable space and time overheads? So before delving into quantum computation, so we'll look at some of the basics of quantum computation. The information unit in classical computation was bit. So in quantum computation, we call an information unit as a quantum bit, or qubit for short. And before introducing qubit formula, let us look at polarization of light. So polarization of light or electromagnetic wave is the direction of the electromagnetic field. So, for instance, we have an electromagnetic wave here, which is propagating in the x direction, and electric field, you can see it oscillates along x direction. So we say that that this electromagnetic wave is polarized along the y-axis. So that's not only possible way an electromagnetic wave can be polarized. So we can have linear polarization, for instance, where we can have the electric field vector making an angle pi/4 with both y and z axis. Or more generally, we can have so we can have the electric field making some angle theta with both y and z. The electric field vector making an angle theta with the y-axis. So in which case, so like both these cases are treated as linear polarization. And in this case, we have the amplitudes along the y and z axis to be equal. So they can be unequal. The electric field magnitudes along y and z axis can be unequal, and there can be a phase difference between them. So that's accounted for by elliptic polarization, where we have unequal amplitudes for electric fields, and they can be off, and those and electric field components along y and z axis can be off by a factor of delta. So there can be a phase difference of delta between the y and z components of electric field. So we have this polarization of light. So we can pass it through an object called polarizer. So this polarizer is a material which which allows only light with a specific polarization to pass through. So this polarization has certain, so it has a certain axis, and if the polarization is perfectly aligned along that axis, it lets the light pass through. So if the input intensity is I naught, the output intensity is also I naught. So what happens if this axis makes an angle theta with electric field? So in that case, a fraction of the light passes through. It passes through, and a fraction of that, and a fraction of the input light is reflected back. So if the electric field makes an angle theta with this axis, then the output intensity along this direction is going to be I naught cos square theta, and the reflected light will have an intensity I naught sin square theta. So this is all standard optics that we know from high school. And the polarization of this light which passes through is same as that along this axis, and the one that's reflected here, so that will have a polarization which is perpendicular to this axis. So we know that that light sometimes behaves as particle, and certain phenomena like photoelectric effects can be explained only if you assume that light is made up of particles called photons, and we can ascribe certain wave-like properties to the photon, like wavelength, polarization, and so forth. So the polarization of a photon is simply what so it's the same as what was assigned to the beam of light previously. So we can so we have this classical experiment where we had polarized light passing through a polarizer. So what happens to this picture when we assume so if we assume that we have particles here, photons here instead of an electromagnetic wave, and you can think of this light source as emitting a certain number of photons at any given time. So to do that, so let's assume we have a single photon source. So this a single photon source can actually be created in time. You can reduce the intensity of laser to low levels, to very low levels, so that it emits just one photon per unit time. So suppose we have such a single photon source, and we allow it to pass through the polarizer. So in this case, we have this polarizer axis aligned perfectly with the polarization of the photon. So the photon will simply pass. So it will simply pass through the polarizer as if there is nothing. And suppose if we take so if you rotate the polarizer such that it makes an angle theta with this polarization, then what happens? So in classical picture, we had I naught cos square theta intensity of light passing through the polarizer, and the other part which gets reflected. But photon is one entity, and you can't split the photon into two. So it should either pass through the polarizer, or it should just get reflected off the polarizer. Is there a question?
No, I have muted all. I think there was some disturbance, so I muted everyone.
Okay, no problem. So if the photon, so if the polarizer makes the angle theta with the polarization of the photon, then we have the photon either going through the polarizer, or it gets reflected off the polarizer. So this is something which is not found in classical. So it's something which cannot be explained by classical picture. So you can repeat this experiment with any number of photons. Suppose you send some n photons through this polarizer, and if you put a detector here to see how many photons went here and here along this straight path and along the reflected path, and then you will roughly find that. So you'll find that roughly n cos square theta photons pass through the polarizer, and then sine square theta photons were reflected. So it exactly reproduces what we obtained in the classical side. That intensity will be proportional to cos square of the angle when it passes through, and it's proportional to sine square of the angle when it gets reflected. Sorry, there's some issue with moving this. How do you get rid of this?
How do you get rid of what?
This pen stuff, which is
Pin.
sorry. So give me a minute. I'm not able to move.
Yeah,
to the
it has
next
moved. The
slide.
next slide has come. I think something. No. It's still in the same slide.
Yeah.
Maybe you can stop sharing and try to again reshare. Maybe.
Okay. Yeah. Let's went through. So now we can ask a question. So what's the polarization of the photon once it passes through the polarizer? So what we can do is we can put another polarizer here and check the polarization. And this polarization axis is perfectly aligned with. Sorry, I should have shown it perfectly aligned with this axis. So if it's perfectly aligned with this axis, then the photon will simply pass through. So it simply passes through this polarizer without any hindrance, which means that the polarization of this photon is exactly is exactly what is dictated by this axis of the polarizer. So the one which is reflected, again you can put the polarizer with axis which is perpendicular to the axis of this polarizer, and you will see that this photon just passed through this, which indicates that the polarization of this photon is exactly perpendicular to this axis of polarization. So this this brings forth the question that does each photon have a polarization along the axis or perpendicular before the measurement? No, because you can. So if you have this photon which passes through, so which is emitted from this source, and you can check the polarization of this by putting a polarizer with axis perfectly aligned to this known polarization, and this photon will. So the photon will perfectly pass through. So the polarization of photon is exactly similar to the classical beam of light without the measurement. So how can we explain? So what we saw just now. So when you make a measurement with this polarizer, so this measurement forces the photon to take polarization to be exactly along this polarizer axis or perpendicular to it. So we can say that the polarization of this photon is a sort of a superposition of this state, which is the axis of polarization, or its reflected state, or the reflected state of the polarizer. So we had this polarization which was cos theta. So which was cos theta and sin theta along y direction and z direction. So here y and z represent two different polarization or two different possibilities for the polarization, and the photon polarization here is a superposition of these two different possibilities. Okay, and the measurement gives just one of the two possibilities, which are dictated by the coefficients. So we saw that this photon polarization is inherently probabilistic. So there's nothing fixed about the polarization when you're measuring this. And depending on the angle of the polarizer, it can give two different possibilities, which are dictated by these coefficients cos theta and sin theta. And this polarization of photon is an example of qubit. So photon polarization is a qubit. So the photon polarization of a photon is an example of a qubit. So we can formally define a qubit now. So in case of polarization, we had two different possibilities. One was one was polarization along y-axis. The other was polarization along z-axis. So we can represent these polarizations with this notation. And this is called a get. And we pronounce this as get 0 and this as get 1. So polarization of a photon can be expressed as a linear combination of these two, of get 0 and get 1. So in general, the qubits, so we can see that these coefficients are, so in general, we can represent a qubit state as a superposition of two states, 0 and 1. And these coefficients A and B, they are complex numbers, satisfying the constraint that sum of their modulus squared is 1. So the sum of modulus squared is the probability that you obtain 0 when you measure this qubit. And mod B squared is the probability that you obtain state 1 when you measure the qubit. So using polar coordinates to represent these complex numbers, you can write A as R1 as some R1 e to the I phi 1 and B as some R2 e to the I phi 2, and then you can factor out this phase e to the I phi 1, and we are left with the state which resembles this state, cos theta 0 plus e to the I phi sin theta 1. So this phase which appears outside, so this is called global phase, and this is generally not an observable. And by an observable, I mean like you can't estimate this phase by any experiments. And this phase can be, so the phase difference phi 2 minus phi can be estimated by interference experiments in the lab. So the other quantity which is associated the qubit is the conjugate transpose of a state. So the conjugate transpose is defined by changing all the complex coefficients to their conjugates. So by changing all the complex coefficients to their conjugate, and these are column vectors. So here, so this 0 will be a row vector 1 0, and 1 is again a row vector 0 1. And you can see that these two states are orthogonal. Orthogonal meaning their inner products vanish when there are two different states, and their norm is 1. So this states, so this set of states called orthonormal states. Yeah, and if you look at so as you can see, the state of a qubit is a complex vector, and you can compute the norm by taking the inner product with its complex conjugate. So in which case you find that it's 1, and because we constrained the coefficients A and B to have this property. So these quantum states are norm 1 complex vectors. So examples of qubits, so you can find, so there are several realizations of qubits across various platforms. So one of the realizations is in neutral atoms. So in neutral atoms, we use two predefined energy levels. One is called the ground state, and the other is called the excited state. And you can create superpositions. So you can prepare that in the superposition of these two states. So one of the states, say the ground state is represented by 0, and 1 we can use to represent the excited state. The second example is spin systems. So subatomic particles, they behave like tiny magnets, and when you put them in an electric, so when you put them in the magnetic field, they can align themselves either along the direction of magnetic field or opposite to it. So you have two levels here. So one level or one state is along the field, and the other level is opposite to the field. So one of the examples where spin is used as a qubit is in nitrogen valency centers in diamond. So diamond is made up of carbon atoms, and if you remove a carbon atom and instead put a nitrogen atom there, like you'll have one electron on nitrogen atom which is free, and the spin of that electron is used for encoding quantum information. The other example is nuclear magnetic resonance, where the magnetic moment of certain atoms of nuclei of certain atoms are used for encoding quantum information. And the third one is superconducting qubits. So here, so when you cool down certain materials like aluminium in a specific way, you will have so if the temperature is below a certain threshold, then you have a current which goes through that circuit of superconductors, and that current can either be in the clockwise direction or anti-clockwise direction. So again, you have two states for the current here, which represent two states, 0 and 1. So far we described one qubit. How do we describe the series of two qubits? So again, we can go back to the experiment where we had a photon source, and instead let's assume that it emits two photons with the same polarization at the same time. And the axis of this polarizer is again at an angle to the polarization. So here we can have four possibilities. So the two photons can simply pass through. The polarizer as here, or one of them just passes through and the other one just gets reflected as here, or both of them can get reflected. So this gives us four possible states for two qubits. So the first state is represented 0, 0. The second and third state are represented 0, 1, 1, 0. And the last state is represented as 1, 1, meaning that both photons are reflected. So in general, the state of two qubits can be represented as this complex vector, where we have superposition of four different possibilities. And here the coefficients obey the constraint that sum of their modulus squared is 1. So how do we mathematically describe two qubit states? To do that, we need something called Kronecker product. Suppose that we have two matrices A and B, and we don't care about the dimension. So these can be row vectors and column vectors, or they can be any m cross n matrices. The Kronecker product is described of two matrices is described as A tensor B, which is simply you take A11 and multiply by B, and you take A12 multiply by B, and so forth. And you do this for all coefficients of A until you get some A m cross n times B. So if you have A as an m cross n matrix and B as some P cross Q matrix, this Kronecker product will have dimensions MP cross NQ. So 2 qubit states can be obtained from 1 qubit states. So let's take the Kronecker product of 0 0. So that gives us 1 0 tensor 1 0, which gives us exactly this state. So 1 times 1 0, 0 times 0 times 1 0. So this precisely gives us this state, which is 0 0. So just 1 followed by 3 zeros. So we have 4 coefficients here. So it's not necessary that all those 4 coefficients should be non-zero. So for instance, I can have the coefficients A2 and A3 becoming 0. So in which case we get the state A00 plus B11. So this is not a usual quantum state in the sense that if you measure just 1 qubit, so suppose I measure 1 qubit, the first qubit, then the second qubit and obtain some outcome, let's say 0 or 1. So I have state phi. So I have state phi, and I measure qubit 1, and say I obtain outcome 0. So if I measure after this, if I measure qubit 2, I'll not get outcome 1, but I'll always get outcome 0. So this is sort of counterintuitive. So it's counterintuitive, and Einstein famously called this process as a spooky action at a distance, where the measurement outcome of one somehow affects the measurement outcome of the second qubit in the state, even if they're separated. Even if they're separated spatially. So such states are called entangled states, and these entangled states are one of the resources that we use in quantum computation. And states which cannot be written in this form are called product states. For instance, if I just make A1 and A2 non-zero, and if A3 and A4 are 0, I'll get the state 0 tensor. And if I assume that A1 and A2 are the same, then I can write this down as 0 tensor 0 plus 1. So this is kind of factoring the states of 2 qubits. And if you can write the state of a qubit in this way, you call such states as product states. Yeah. So far we described how to. So far we saw how to describe the state of a qubit, and we have to do operations on those qubits in a similar way that we do operations on classical bits. So recall that qubit states are complex vectors, and we can perform operations on them by multiplying by complex matrix. So let's say the complex matrix is denoted U and has 4 elements, A, B, C, and D. So we require that the state after we do the operation should be still a valid state. By valid state, I mean if the norm of this so if the norm of this state is still 1, then we call it as a valid state. So if we look at the norm of this, so if we impose the condition that norm of the state after the operation should be 1, we get the condition that U dagger U should be identical. So U dagger is defined similarly. It's a complex conjugate where you take the transpose of U and then conjugate all the. So if you look at this condition, you'll get that norm of this column should be 1, which is shown here. A norm of this second column should also be 1. And if I take the inner product of these two columns, I should get 0, which means that these two columns should be orthogonal to each other. So if you look at how this operator U acts on the basis states, it simply maps. Zero state to the state whose coefficients are A and C, and it maps 1 to the state whose coefficients are B and D. So since this should preserve the norm, and it should not change the angles between two orthogonal vectors. So we have 0 and 1 mapped to two orthogonal vectors, and these may be called unitary. So this matrix maps orthogonal states to orthogonal states. So we can look at some examples of unitaries which we encounter often in quantum computation. So because quantum states also have zeros and ones, so one operation which is similar to the classical in the classical bit flip operation is just to swap the two states 0 and 1. So if you look at the operation of bit flip, it simply changes the probability. So it simply exchanges these coefficients A and B here. So this means that if I measure this bit flip state, I'll obtain a 0 with the probability mod V square, and I'll obtain 1 with probability mod A square. So these probabilities are sort of swapped for zeros and ones. So we can give a matrix representation for this bit flip operation, and for matrix representation we need a basis, and we choose this basis as 0 and 1. And in quantum computation, this is often referred to as a computational basis. So because of using zeros and ones. So we had the requirement that x0 should map to 1, and 1 is 0, 1. So as we saw before, this should be equal to the column vector AC in the matrix U. So you get 0, 1 here as the first column. And similarly, the condition that it should map 1 to 0 imposes, so it gives us 1, 0 in the second column. So we have a matrix representation for X. So now we can ask if there are any states which are left undisturbed by this operation of bit flip. So such states are called eigenstates. And let's consider an equal superposition of 0 and 1, as I have given here. And this is a special state, and it's called a plus state. And you can take the other state where the phase of 1 is flipped, and that's called a minus state. So if you apply bit flip operator to plus state, so it simply leaves it unchanged, because x0 gives you 1 and x1 gives you 0. So the state is left unchanged. So the plus state is called +1 eigenstate of the X operator. So and similarly, if you look at the operation of minus state, operation on minus state, you'll see that X operator simply flips the phase of 0. So because x0 is mapped to 1 and x1 is mapped to 0, the phase of 0 becomes minus, and if you factor out the minus sign, you get minus of the minus state. So therefore, so this state is the -1 eigenstate of the X operator. So we have another degree of freedom in case of, so we have A0 plus B1. So what we can do is we can flip this phase by 180 degrees. So if we flip this phase by 180 degrees, so this should go to A0 minus B1. So this is called phase flip in the literature. And again, and its matrix representation simply 1, 0, 0, minus 1, because we are choosing the eigenstates of Z as computational basis. And note that the operators Zx, the operators X and Z do not commute. So we had bit flip operation and we had phase flip operation. So we can have an operation which combines both of them. So in that case, we should get 0 going to 0 going to identity I1, whereas square root of -1. Where I square root of -1, and we have 1 going to -1, so 1 going to -I0, and this matrix can be obtained as a product of X and Z operators along with this additional phase factors. So the operators X, Y, and Z, along with this identity operator, which is multiplied by the phase factor I, they form a subgroup of unitaries for 2 by 2 unitaries, and this subgroup is called polygroup, and its description is as below. And note that the operators X, Y, and Z are their own inverses. So for instance, if we take so just take operator X square. and if you multiply, you get identity. So now we'll look at other non-trivial operations on the qubits. So earlier we saw that we could change this relative phase factor by 180 degrees. So can we change it by 90 degrees? So if we have to change it by 90 degrees, we have to introduce a phase factor I to this. And operation that does this is called the phase gate. And it has a diagonal representation in the computational basis with elements 1 and I, the phase factor I. The second such non-trivial operation is what corresponds to a Fourier transform on two entries. So on this gate is called Hadamard gate, and this matrix representation is given here with 1 1 along. So with 1 1 for the first column and 1 minus 1 for the second column. So this Hadamard gate is used for changing the basis of measurement or for transforming states from 0 to plus states or from 0 to minus states. So if you look at the action of H on 0 state, it simply maps 0 state to plus state and 1 to minus state. And it's also useful for creating superpositions of bit strings. So for instance, if I start with the state 0 0, and if I apply Hadamard on both qubits, then you can write down the resulting state as tensor product of 2 plus states, and I can further expand this, and this just works like multiplication, and you can just combine 0 0 and get the state 0 0. You can combine 0 1 and get the state, and you can combine 1 0 and get the state 1 0. You can combine states 1 and 1 and get the state. So this is one of the things which is used in quantum algorithms to prepare an equal superposition of all bit strings. So far we looked at operations which acted on only 1 bit. So now we can look at operations which act on 2 qubits. So here is an example of such a 2 qubit gate, which is called the C0 gate. So it takes 2 qubits. So let's say psi1 and psi2. So one of them is used as a control qubit. And this is called the target qubit. So this action on the basis states is to flip the state of the target qubit depending on the state of the control qubit. For instance, if the control qubit is 0, and if I have A0 plus B1 here, then the output is going to be A0 plus B1. It's left unaffected. On the other hand, if I have state 1 here, so the output is going to be B0. Sorry. So it's going to be A1. It's going to be A1 plus B0. So it applies X gate on this target depending on the value of this bit in this state. So you can use the CNOT gate to create entangled states by proper choice. So if I take plus state here, so if I take plus state, and if I take 0 as the target qubit, so plus state is 0 plus 1 over root 2, and have this tensor product. And when CNOT acts, you get 0 0, and because there is a 1 here, the state 1 0 will get mapped to 1 1. So we'll get 0 0 plus 1 1 over. So we have an entangled state here. So these two qubit gates can create entanglement, or they can also break entanglement. So for example, if I apply CNOT gate in on this entangled state, the state 0 0 is left unaffected, and here the control qubit is 1. So that will flip the state of the second qubit, and I'll get 1 0, which is simply the product state of plus and 0. So the gates that we described so far, namely phase gate, Hadamard gate, and CNOT gate, they leave the polygroup invariant under conjugation. So what I mean by that is, if I take the poly Z operator, and if I conjugate it with a Clifford element here, I'll get back a Clifford. I'll get back a poly operator. So the phase gate. So the phase gate does nothing to the Z gate, because phase gate is diagonal, and Z is also diagonal. So Z is left invariant by phase gate, but it swaps X and Y. So it interchanges X and Y operators. So similarly, if you look at Hadamard gate, so Hadamard simply swaps X and Y operators, and because X and Y operators are swapped, Hadamard gate leaves the operator Y invariant. And similarly, you can look at CNOT gate. So CNOT gate. So this is control qubit, and this is target qubit. So Z operator of control qubit are left unaffected, whereas X operators on control qubit, it spreads to control qubit. And, so it spreads from control qubit to target qubit, giving us the product of these two operators, XC and XT. And similarly, Z on target qubit spreads to the control qubit C, and X operator on the target is left invariant. So this action. So this is something that we care about in quantum computation. So if I have an X error on control qubit, that X error also spreads to the target qubit, and so forth. So the action of these gates on the poly group is simply permutation. So they swap the poly operator to another poly operator and leave some poly operators invariant. So you can just track the action of these gates by simply looking at how the operators change on the qubits, and therefore we can easily simulate any circuit which consists of Hadamard phase and CNOT gates efficiently on a quantum computer. All you have to do is just track. All you have to do is just track these how these operators are modified by the operation. So there is another class. And this class of gates is what are called different gates, and they form a group under composition. So there are other class of gates which are called non-clifford gates, and these gates do not preserve the polygroup under conjugation, and therefore these gates cannot be simulated efficiently on a classical computer. An example of this family of gates is what is called the T gate. And this T gate has matrix representation which is diagonal, and the elements are 1 and e to the I. So this simply changes the phase factor by e to the I by 4. The other class of gates that we described, the preferred gates, they are sort of easy to implement on the architecture by operations which are native to the hardware. But this set of gates, the non-preferred gates, so they are not so easy, and they're usually implemented by using special states, which are called magic states. And then we use different operations to implement these gates on them. Yeah. So the magic state implement the T gate is given here. So so this has a phase e to the I by 4 on the state 1. Sorry. Just give me a minute. Yeah. So now we can move on computation. So we can see how we can implement certain classical functions on quantum computers. So as a sort of toy example, so let's consider finding the parity of all length 4 bit strings. So here, so the first stage is we have to prepare these qubits in a superposition of bit strings, and I have 4 0 states here, and I've applied Hadamard gate on them. So this creates a superposition of all bit strings. So once the bit string, and then I have an additional kind of scratchpad qubit, which is used just during computations and doesn't carry any information. And now I can perform a CNOT gate from each of these qubits to this qubit. And this qubit has a name, and it's usually called the ancilla qubit. So suppose we have a state which has an even number of ones. So example, let's say 0010, and then we can take the Sansela state. And then if I apply a C0 gate, the first qubit will not flip this state. The first qubit will not flip this state, but the second qubit will flip the state to 1. And the third qubit will also flip the state. So effectively, we have the state unchanged because of the C0 gate acting on qubits 2 and 3. And again, the last qubit will not flip the state. So if a bit string has even parity and you do a C0 operation, the state of the Sansela qubit remains unchanged. On the other hand, so let's take a bit string with an odd number of ones, and then see how this C0 action goes. So the first qubit will not flip this state. The other 3 qubits will flip this state. So since the state of the Sansela is flipped thrice, it goes from 0 to 1. So this set of C0 gates is what we call UF, which means the unitary operator, which performs the operation f of x on these bit strings. So after we do this operation, we have a sort of entangled state here. So we have gates with odd number of ones, tensor 1, and all states with even number of ones, tensor 0. So this is an entangled state, and if you measure the Sansela qubit, you either end up getting all even states or you end up getting all odd states. So this looks like this is not much useful. But we can use this technique to find some global properties of f of x, and we cannot use this to find all values of f of x. For instance, so by global property, I mean to know whether f of x has f of x is 0 for all bit strings, or f of x is 1 for all bit strings, or whether f of x is 0 for like half of the bit strings and 1 for the remaining bit strings, and so forth. So quantum algorithms just try to look at such global properties of classical functions and not individual evaluations. So as an example, let's take the first quantum algorithm that was proposed. And this was designed for a very specific function. So suppose I have some function f of x, and I want to know whether f of x is 0 for half of the bit strings and whether it is 1 for others. So this property is called balancing. So if f of x is balanced, we have a 0 for half bit strings and 1 for the other half. So suppose we have a unitary UF, which can evaluate as the function f of x. And this function, or this unitary UF, is created as a product of Clifford and non-Clifford Clifford and T gates. So we can have a series of Clifford and T gates which can implement this specific function U of f. And so let's suppose that we have this U of f with us. And I'll prepare 2 qubits. So here I'm taking just one bit. So I have 2 qubits here, 0 and 1, and I apply Hadamard gates on them. So the state here will simply be plus minus. So 0 is transformed to plus state by Hadamard. So it is plus state on 1, and 1 is transformed to minus state. So it is minus on the second qubit. So you can write this state as a superposition, 0 minus plus over root 2. So this is the state file before the operation is applied. And our unitary UF is such that it takes so it takes x minus state to minus 1 to the f of x x minus. So this is what we desire of this unitary U, and we assume that we have a series of Clifford and non-Clifford operations which can get us this state. So the state here will look like minus 1 to the f of 0, 0 times minus, and minus 1 to the f of 1, 1 and minus. And now what I do is I apply Hadamard on the first qubit. So if I apply Hadamard on the first qubit, it should take 0 to plus state and 1 to minus state. So let's call this state as some alpha. So Hadamard on the first qubit, acting on the state alpha, you can note that plus state should be 0 plus 1, minus state is 0 minus 1. This is over root 2 and this is over root 2. So we can write this as 1 over root 2 minus 1 to the f of 0 plus minus 1 to the f of 1, 0 minus state is 1 over root 2 minus 1 to the f of 0 minus to the f of 1, 1 minus. So let's suppose that the function is balanced, meaning f of 0 and f of 1 are the same. If that's the case, when I measure the first qubit in the x spaces, I'll end up getting 0. So if I get state 0 after measuring the x spaces, then that implies that f of x is balanced. On the other hand, if f of 0 and f of 1 don't have the same value, then I'll have this state. So if f of 0 and f of 1 have different values, then this state vanishes, because f of 0, so let's say if 0 is 0 and f1 is 1, then this amplitude vanishes, and we get only this amplitude. And therefore, the measurement outcome will just give 1 if f of x is not balanced. So this illustrates that you can do certain classical computations to know certain global properties of classical functions by using quantum circuits. So by using quantum computation. So there is an n-qubit version of this. So there is an n-bit version of this algorithm, which is called Deutsch-Jozsa algorithm, which which does the same. Is there a question?
Oh, some disturbance. I muted all again. Yeah.
Okay, thanks. So if X bar is an n bit string, then we have what is called Deutsch Jausa algorithm, which does the same but takes so instead of 0 here, we'll have 0. So we have n0 states here. So the advantage of this algorithm, so advantage of quantum computation actually comes here. So if classically, if you want to know if a function is balanced or not for n bit strings, so typically you have to go over at least 2 to the n by 2 bit strings. Like if you have to evaluate, half of the bit strings and find out whether they're 0 or not. So the complexity of classical operation for doing that is 2 to the n minus. But when you so if you run Deutsch algorithm, you can get it in just one shot. So you don't have to do 2 to the n minus 1 computations to find if the function is balanced or not. So if you run this algorithm once, like you will know if the function is balanced or not. So the advantage of quantum computations, like you can find in such situations. And there are other algorithms like Shor's algorithm, which can efficiently factor a given number into 2 primes. So, but that's a bit involved, and probably will not take it up. Okay. So there are some key differences of quantum computation with classical. So one of them is a superposition, where we can prepare quantum bits in a superposition of different states, unlike classical states. And the second one is entanglement. So this is a highly non-classical property of quantum systems, which is usually exploited during computations. And parallelism. So this is sort of preparation of states which are in superposition of bit strings. So all these factors kind of give us the advantage in quantum computation. So to summarize, we introduced concept of a qubit and its realization across various platforms. And we also discussed qubit operations, how we manipulate the qubit states and so forth. And then we also saw examples where we can employ qubits to solve certain classical problems efficiently. So the next question is, how do we implement, so qubits are inherently noisy. So how can we perform these computations efficiently the presence of noisy qubits? Thank you.
Thank you, Dr. Manoj. At what time shall we reconvene for the next?
So it's 3:20.
Yeah.
So probably we can take some 15-minute break. 15 or
So
20 minutes.
3:45 will be fine. 3:45.
Yeah, 3:45 should be good.
Okay, thank you. Okay, dear participants, we will again have a session by Dr. Manoj at 3:45. I will share his feedback form maybe at around 5 o'clock after the session gets over. Thank you. We will reconvene at 3:45.
Thank you. Being so they are the state of art, and so the industry is turning away from surface goods to quantum DPC goods. So one of the reasons is surface codes can include only one logical qubit. So this kind of gives large qubit overheads if you're implementing some big algorithms like Shor's algorithm. So that's why so we are moving away from surface codes to quantum multipc codes, where we still so we're still the check weights are sort of low, and we don't have this nearest neighbor connectivity constraint for them. So so Google is one of the companies which is pursuing surface codes for a long time, and they have been able to show error correction, repeated error correction for a longer duration of time. And if I remember correctly, they also implemented some small algorithms, I think, with surface codes. So that's sort of the state of art right now. So so we are still dealing with very small quantum codes. So,
For your answer, and thanks for the nearly 3 hours you spent despite your fever and being a bit under weather. Yeah, thanks a lot. Thanks a lot for your time. Thank you, Dr. Manoj, for joining.
Thanks, Darshan, for the invite.
So we have our next speaker, Dr. Mustafizur Rahman from IBM, who has joined us. Welcome, Dr. Mustafizur. Swarnima, can you please introduce the speaker?
Hello, thank you, sir. For our next session, we have Dr. Mostafizur Rahman, who obtained his master's and PhD degree from IIT Kharagpur. He is the recipient of the PMRF scholarship. He has been a visiting faculty at SN Bose National Center for Basic Science and a visiting scientist at
Mute.
Am I audible?
Yeah,
Hello.
please. Yeah, you're audible.
He is a recipient of the PMRF scholarship and has been a visiting faculty at SN Bose National Center of Basic Science and visiting scientist at AICTE in Japan. He is presently a research scientist at IBM Quantum India. He has authored numerous papers and has contributed to multiple patents. It is our distinct pleasure to welcome you, sir, for delivering a lecture today. Hello, sir.
Thank you so much for the very kind introduction, and thank you for inviting me to this prestigious program at NIT Trichy. Shall I start or?
Yeah, you can start, sir.
Yeah, sure.
You are made as a presenter. You
Yeah.
can share your screen.
Is this visible?
Yeah. Please continue, sir. Over to you.
Yes.
Thank you.
Yeah. So to the audience, I think most of you are faculty members. So please feel free to stop me any time you feel, or you can also put your question in the chat box. So I'll be trying to answer the questions while I'll be covering the topics. So I think this FDP already it is covering the basics, right? So I won't go too much of the basics. So probably I'll give you some flavors. What is the state of the art currently in industry, especially around quantum algorithms. And also I'll talk about certain complexity aspects, why some problems are interesting or important in quantum domain, why shall we at all care about quantum computing. And then I'll also talk about the utility and the something what is called the quantum advantage for what we are looking for. Right? So why do we need a computer at all? So I'm just going a bit slow. You can feel free to ask any question. So of course we need computations, right, for to solve problem faster. For example, if you want for some engineering problem, you need a matrix inversion. Just beyond 4x4 matrix inversions doing on hand is very it's intractable, right? You need a computer. So similarly, there are problems. For example, you want to simulate the 100 particles to understand the behavior of certain matter or certain materials, right? So it is impossible even by today HPC, because the computations that runs on the HPC, right? For example, if you want to understand, okay, if I take a cup of coffee, okay, so then what will be the impact in my body in terms of my mood change or attitude change, or how do I feel? So these are typical abstract questions. Even in fact, you just try to understand how the dynamics of caffeine molecule works in our body, and just try to considering its just 24 electronic with 50 spin orbital configurations. You have 2 power 50 complex computations. So another example might be if you just eat certain food and there is some enzyme in our body like the Fimoco complex molecule, and you try to understand, okay, if I take certain food, then how the digestive systems actually works, right? How a particular complex enzyme actually works, right? To digest that particular food. So even these Fimoco molecules with 108 active orbitals requires 2 to the power 108 complex computations, which are the beyond limit of computation. So there are problems which are typically intractable by the classical computer, even supercomputers. So we can think of those kind of problems as a candidate problem for quantum computations. I'll come what quantum computation means. And the typical limit of the today's computer to answer various already arithmetic computations, classical computers are very good at. And typically 1 exaflop computations refers to 10 to the power 18, right? Flops per second, right? Floating operations per seconds. And if you just convert this to equivalently 2 power, so it is 2 power 60 means approximately 60 qubits, right? So you can, there are simulators where you can still run several experiments. Classical computer trained with the behavior of quantum machines, they are classical machines. You can still run maximum up to 60 qubit. That's some approximate figure, right? So what is a quantum computing, right? And you already have a lot of interaction, so I want to cover these qubits and all. Just an analogy, like you prepare the classical bits using the transistor technology on the classical counterpart. Here there are several technologies, and one of them that at IBM we are doing is the superconducting best qubit, right? And these are typically the artificial atoms that we prepare, right, using say some kind of this kind of oscillator circuits with Josephson junction, where we create energy levels, right, in a particular atomic cavity, right? And those energy levels we can control. Suppose we call a ground state as a first level of information to like the first basis to represent information, that is gate 0, and another level we take as gate 1, equivalent to classical 0 and 1. And these are typically vectors quantity. Now you can represent your quantum informations with certain quantum phenomena, such as the superpositions, interference, etc. I'll come later. So typically, this is the like the analogy in how they prepare. Actually, qubit is prepared, right? Second, the mathematical representations, right? These are typical the real number set, right? We represent your the binary bit string like 0 and 1, and here you need to represent in terms of vectors, right? So vectors means any vector, you need some basis representations to represent the vector. For example, 0 and 1, if these are two bases, then you can write this vector, okay, this vector is the some combination of this 0 and 1. So A times 0 and B times 1 is the representation of some arbitrary vector psi, right? Now, so there are certain operations which are important. So I'll just take 2 to 3 minutes to cover the basics, and I'll come to the algorithm part. So superposition is nothing but just it's a vector property, right? So any vector you can represent, say with some coefficient times the basis vectors, right? If you have certain basis vector, for example, computational basis vector like 0 and 1, this 0 is basically 1, 0 vector, and K1 is the column vector 0 and 1. So you can represent in a two-dimensional case any vector as just a combination of these two orthonormal basis vector 0 and 1. Similarly, the same mathematical vector you can also represent in the eigenbasis. Like if you want just convert this vector to another domain, like where the orthonormal bases are eigenvectors, right? Or they can be Fourier vectors with the Fourier coefficients F1, F2. These are the things we already know, right? Or also you can represent in any arbitrary basis sets, right? Orthonormal basis set B1 and B2. So this is all together means that any vector you can represent as a combinations of orthonormal basis set. That's the superposition phenomenon. In Qiskit, suppose you have typically people say, okay, we define qubit, which is a superposition of 0 and 1. Okay, so that's how people define, but in general, this is just a vector. And this vector can take value 0, this vector can take value 1, or just combination of 0 and 1. Suppose you start your qubit with 0, right? And you want to create a superpositions, right? So you need to apply an operation. So that is called a gate operations. I'll come bit detail later. Like Hadamard gate, it is a matrix of 1, 1, and 1 minus 1, this type unitary matrix. And if you apply this to the qubit, which is started with the K0 state, right? So when you apply this on the K0, simply you do the matrix vector multiplication, right? This is a normalization factor. It will be actually so 1 by square root 2, square, I forgot to put the square part, square root part, okay? Just there it is 1 by square root 2, okay? So normalized matrix. Now, if you just simply multiply this matrix times this vector, what you will be getting is another vector, which is 1 and 1, right? So just you can do by hand, and you can check that the value that is coming h times K0 is 1, 1. And 1, 1 state is known as the plus state, or which is actually 0 plus 1, this K0 plus K1. If you simply sum these two, so that means I started with 0, I apply the Hadamard gate, and I create a plus state, which is a superposition of 0 and 1, right? So this is how you prepare the superposition state in Qiskit, right? So that's on our hand, right? And if you do measurement probabilistically and repeat the experiment for, say, for example, 1,000 times, right, or 1,024 times, you can see that how many times this I can see the 0 and how many times I can see the 1, right, information. So you'll be getting a histogram, right? So at IBM, we provide the some software framework called Qiskit, which is a very user-friendly framework to run your programs on a quantum computer. It can be a simulator, it can be a hardware, right? For example, you can try the Stern-Garslich experiment. It's a very interesting and very important milestone in quantum physics, right? In Qiskit, you can try this. So I have provided the link here. Okay, at the end of the talk, I'll be sharing some of the resources. So that I'll be providing through Professor Parthasarathy sir, who are interested to do these things. Now there is some phenomena, that is the entanglement phenomena, right? And you already have you already know, and you already have listened to many like discussions on entanglement, very many contradictions, and many like so one of them is the EPR paradox. So that is a paradox basically, and I'm not going to the physics part. So mathematically, typically, if you have, say, for example, at least two quantum system, and they are in a situation that if you measure one particular qubit, you have almost all information about the second qubit, right? For example, this particular state 0, 0, and 1, 1. So these are two qubits. So two qubit has first state 0, 0, 0, 1, 1, 0, and 1, 1. And in this particular configuration, this is called a Bell state configurations, where if you can prepare this particular state, which is called an entangled bit information, EBIT information, if you can prepare this particular state, then if you measure any qubit, like for example, the first 0 qubit, you have all information about the second qubit, right? So I'll come to that point. So how to do that? So just so initially, if you apply the two Hadamard gate into first qubit, so I'm just approaching my presentation in a bit implementation wise way and the applied way, right? And later I'll discuss some important problems that typically institutes, industries, and organizations are doing that may you may be interested in some of those problems. So how to do this? So not going in detail the mathematics part, but the how it is done actually. So suppose you initiated with two quantum registers Q0 and Q1, and suppose they are initiated with 0, 0 state, right? And you apply the Hadamard. So 0 will become plus state, and this second qubit information will again become plus state. So I have the possible combinations of the quantum basis, computational basis states now, 0, 0, 0, 1, 1, 0, and 1, 1, right? And what I have done initially, all were like 0 and 0 state, but there are 4 possible combinations, and I just applied to Hadamard gate. So mathematically, I have 1/4, 1/4, 1/4, 1/4 probability, ideally, right? So there is a question: at what exact stage in the Stern-Gach-Late experiment does superposition collapse during interaction with the magnetic field? Okay, so this is an interesting question. So there is one small implementation in Qiskit you can look at, and I don't, I am not from the physics background, so I'm sorry. But of course, like, so as per the the conclusion of the experiment is as such that if you do the experiment, intuitively we should get a continuous pattern of the silver atom that we pass through the magnetic fields, right? This is by intuition. But what actually happened is a discrete patterns, right? With the probabilities that we see from the pattern is a discrete pattern, right? That experiment you can repeat on Qiskit, right? Yeah. So I'll be sharing the link. Don't worry. Okay. That's the physics part, but mostly I'm covering from very naive mathematical aspects. Probably that will help all the engineers and the computer science people. I'm just removing all the physics from the quantum computing. Okay, although it's highly dependent on physics, but yeah, for simplicity. So the language of quantum computing is linear algebra, right? And all the operations that we'll be doing, all the state that informations we'll have are vectors, and all the operation we'll be doing are typically unitary matrices for now. Okay, there are non-unitary cases, but in general, when you will be doing quantum computing problems on the hardware, you need typically unitary operations currently. Okay, so so you prepare all the 4 possible state, which is a superposition state, right? Now just remove the second qubit, second Hadamard gate. Like, you don't apply the second Hadamard, you just applied a single Hadamard. If you see the left hand circuit, this part. Okay, so let me check if there is a laser that might be helpful. Pointer option. Yes, I can see now. So if you see this particular circuit, I applied a Hadamard here, and then I applied a controlled NOT gate, C NOT gate. Okay. So those who don't know the C NOT gate definition, so please just Google it, or you can get in Qiskit. I'm telling the philosophy, what it happens. So the first qubit you applied a Hadamard, that means you created. So initially we created 2 states, 0 and 0. And when you take multiple quantum system, mathematically they are written as 0, 0 tensor product. Okay. And when they are 0, 0 tensor product, and now you are applying a Hadamard gate in the first qubit, Hadamard gate converts this 0 to plus state. Plus state means 0 plus 1 by square root 2, this particular configurations. That is the superposition state. Okay. Somebody, can you please mute? There are some noise coming. Okay. So now, there is a operations called the C NOT operations, controlled NOT operation. This is also known as an entangled gate or correlation gate. What it does, the philosophy is that now when you just applied the Hadamard in the first qubit, what you got is that you created a first qubit as plus state and the second qubit as it is. So it is mathematically 0 plus 1 by square root 2 and 0. That means 0, 0 plus 1, 0. If you just simply just remove this bracket, okay, 0, 0 plus 1, 0. Now, when you apply the C NOT gate, the philosophy is that if the first qubit is 0, it does not do anything in the second qubit. But if the first qubit is 1, the control qubit is 1, it flips the second qubit. So that's the philosophy. So identity matrix times 0, that means 0 vector will become 0 vector, and x times the 0 vector, that means flip the 0 vector. X is the Pauli X operator or the NOT gate. This is called a NOT gate in quantum computing, which is a rotation matrix 0, 1, 1, 0. And if you apply this C NOT gate, immediately this 0, 0 will become 0, 0, and 1, 0 will become 1, 1. This 0 flipped. Immediately what happens? Earlier I had 0, 0, 0, 1, 1, 0, and 1, 1 state. But now I have only 0, 0, and 1, 0 state. So 0, 1, and 1, 0 state vanishes. So ideally, I should get double the probabilities of 2 state 0 and 1, 1. So the probability becomes 0.5 for 0, 0 and 0.5 for 1, 1. This particular, after measurement, you can get it, right? This particular quantum state is known as the Bell state. And this particular phenomena is so important, and this is the in fact the fundamental of quantum cryptography. Okay, all the secured communications, everything. And this is even known as the one bit of information, one entangled bit of information. Okay, so this is another important phenomena called entanglement, right? So this is how we prepare entanglement in Qiskit. So this is an example. Okay. Another important phenomena is the interference phenomena. So in physics, there are definitions, but I am telling in terms of mathematics and how they are implemented. Okay. So what it does, in interference, you have multiple signals. They do interfere each other, and you get a basically interference pattern in the overall amplitude of the two signals, right? In the resultant vector, right? So that is what we learned in physics typically, right? So let's take an example. If you look at most of the quantum mechanics or quantum computing problem, the heart at core, there is a equation that H psi equals to E psi, this particular equation. And these equations, you don't need to remember from physics side. This is, we know from our 10+2 standard, this is known as eigenvalue equation, right? Matrix times a vector, scalar times a vector. If the vector is same, this matrix operate on that particular vector, non-zero vector K psi, such that there is only a scaling or stretching of that particular vector and does no angular changes, right? That is called the eigenvalues and eigenvectors, right? And once you have this H psi equals to E psi equation, and most of the places, because any physical quantity that we observe, for example, displacement, the energy, the momentum, they are the eigenvalues of some observable, we call Hamiltonian, right, H. And once you want to simulate this problem on a machine or on a computer, right, especially when it is a quantum computer, so this H has to be, so if you solve this equation, in fact, if you write this equation from the Schrodinger equation and solve it, that is a ordinary differential equations. So you can get the equivalent form U, this psi equals to lambda psi. These are two equivalent equation where U is your time evolution matrix. So I'm not going detail. So typically, if you have a Hamiltonian equivalent after the Schrodinger equation solution, whatever you get, that your evolved state is basically e to the power IHT, right? That is a unitary matrix U, right? And you have particular eigenstate and you have an eigenvalue and that particular eigenstate, right? So this is at the core, because you want to measure a particular quantity, that is the eigenvalue of some observable, right? That is the philosophy. Now, the question is, you have an original representation of your system, and you are converting that to the eigen system, right? So, in what typically we look in the eigen system is the correlations, right? So, in principal eigenvalue. So, in PC algorithm, principal component analysis, you have seen that in the principal eigenvector we have most of the informations, right? In the second principal, you have quite less. So, there is a correlation. I mean, how concentrated the information of correlation of two particular phenomena, right? Or a statistical phenomena you can measure, right? So that is also an interference phenomena. Now the question is, what typically we do in interference? So like the last example, if we look at in the entanglement pattern, we had 4 probability states, superposition state, and I created already an interference, right? In that particular interference, the second and third 2 probabilities for the 0, 1 and 1, 0 state are vanished. Only the first and fourth vectors are there with this particular circuit configuration. And this very special interference is called the entanglement, right? This is already a special case. Now, can you do a quantum circuit or some mathematical operation such that you can manipulate this probability mass functions, PMF, from the pattern P1 to P2, for example, right? So there is a circuit now. Suppose forget about this step number 2, 3, 4. Only look at problem number 1, like step number 0, 1, and 2, up to 2. What are the mathematical steps? So step 0, of course, instead of 0, 0, you have taken 0 and psi. So 0 and psi is your first initial state. Then you applied the Hadamard. So your first state becomes plus and psi state. Then you apply the second state, you applied a controlled unitary instead of control not gate, you applied the controlled unitary gate, right? So the philosophy is very similar. If you have a 0 qubit in the first configuration, it does nothing. If it is the qubit is 1, then there will be phase will be added, like added in a sense, it will be a unitary matrix whose phase is added. For example, this looks like this. So if you look at this particular equation, so 0 psi will become 0 psi because the first qubit is 0. It does nothing to the quantum state psi. If the first qubit is 1, it does a matrix multiplication u times psi. Now this matrix, suppose 1, 0, 0, e to the power I theta, then it will be e to the power 2 pi I theta get 1, right? Like that. So I just, this is just a like concentrated like equation, right? You can break it and do it. So now, once you do that, immediately what you can see, I have what are the states, possible states. Suppose if my gate psi is alpha times gate 0 plus beta times gate 1, then you have created lots of possible states like 0, 0, 0, 1, 1, 0, 1, 1. You have created multiple possible probability amplitudes in front of them, right, as coefficients. So this is how we actually manipulate probabilities in quantum algorithms. These are fundamental. Now, this particular configuration, when you apply another Hadamard, this entire configuration is called a circuit for expectation calculation. Up to 2, like this H and U, up to stage number 2, this particular configuration is called the quantum phase trick circuit, which is a fundamental to quantum phase estimation, quantum Fourier transform, as well as source factorizations algorithm. I mean, instead of explaining algorithm, I am just telling how the algorithm works in quantum computing regime. Okay. And just by adding another level of Hadamard, what you do, you again, second level of manipulation you do on 0 and 1 state. 0 becomes plus state and 1 becomes minus state, right? And just you need to do mathematical projection to retrieve the probability of 0 and 1, right, state. So you'll be getting the expectation values, the real quantity psi u psi, this expectation value, and the 1 minus real quantity psi u psi, another quantity. You can additionally apply a phase gate here, 90-degree phase gate, you will be getting the imaginary component. So this is how we calculate the observable, given the observable say u and a particular vector psi, how to compute the expectation value, psi u psi, right? So this is a circuit for that. And what typically we have done here, the interference, right? Okay, I'm just keeping all these stories like end of Moore's law, semiconductor, these things I'm just keeping for the sake of time. Well, so what typically we do, those who are from the electronics, electrical, or the computer science, so and probably even one of you might be feeling that this is my first session I am attending quantum computing. Okay, there is room for you, no need to worry. Just assume that in classical computation you have some information, binary bit string, and you have played with the binary bit string using AND or NOR, NAND, XOR, this kind of operations, right? And you have applied these on digital logics, as well as there are matrix representation for these gates as well, right? So that's how you do with the classical information. Similarly, in quantum, you have information as vector, and your operator, any operation you want to manipulate on the informations, right? You want to retrieve some information, you want to transform a vector to another domain, right? For example, Fourier transform, anything you want to do, right? For classification also. I'll come to the example of classification like the support vector machine later. So typically what you need to do is construct a unitary matrix, and that unitary matrix can be broken into Clifford and non-Clifford gate sets. So just write down the term Clifford and non-Clifford. I'm not explaining, but the Clifford gates obey the Clifford algebra. For example, the Hadamard gate, Pauli gates, these are called the Clifford gate. And non-Clifford gate is the T gate, that is another gate that is also used in formation of the unitary matrices, right? So these are typically gates, and one of the important property of this gate that they are the unitary matrix. So unitary matrix means U star U equals to U star equals to identity matrix, means U star equals to U inverse, right? Self-invertible matrix. Now, so that means the logic that you need to operate on the quantum information, they are reversible logic. That's an important statement. Okay, there is a question. Sir, could you discuss the experimental limitation in scaling Bell state based? Okay, so maybe I can discuss, but I prefer that I have taken a number of lecture series in quantum communication with MNIT, this AICTE. So I'll be sharing, sir, those links. Maybe you can look at the details of their GHZ state and all and their implementations. So I'll be sharing. No worry. Okay. Okay. Now let's come. Noise is coming. Okay. So now let's now talk about where are we presently standing, right? In terms of let me get the chat box also. Sometimes it's disappearing. Okay, thanks. Okay, so now presently we are working on a particular era we call the utility era. That means I have a problem. The problem, what type of problems I'll discuss. Now that particular problem, earlier we were doing certain things like basics things, right? And theoretically, we have algorithms like the HHL algorithm, Harrow-Hasidim-Lloyd algorithm for linear system solving, or the source factorization algorithm to like factorize big prime numbers, right? So which has security implications, right? Those are the fault tolerant algorithm. But do we have some algorithms which we can use on real world applications, right? So those kind of applications we do, and those kind of applications currently we are calling the utility experiments, where you have a solution of the problem. And even if the solution does not beat the classical one, but it competes with the classical one at a very high, large scale, like around 100 qubit or so, like large scale applications, right? And we expect that by extending the problem in the near term, where we have a good error mitigation techniques and the upcoming error correction techniques, we'll formulate some problems or we'll solve the problems where a regime classical can never reach. That particular regime we call the quantum advantage. So at particularly in this particular era, that's quantum utility era, right? So IBM currently has 156 the Heron processors in IBM system 2. And this is a typical like the characteristics of a particular processor. For example, when I talk about a particular processor, it has some two different types of gates we use. One is called the single qubit gates, another is the 2 qubit gates. For example, the CJET is a 2 qubit gate, right? RJET is a single qubit gate. And 2 qubit and single qubit gates, they have a error, like they have some like, because they are the physical qubit, they have some at the hardware level, they have certain errors and coherence time, right? There are two particular parameters for the coherence time, T1 and T2, and these are like 261 microsecond, 150 microsecond. These are the typical coherence time parameters, T1 and T2, right? And how many operations you can do with the 156 qubits is 340k. That is the in 10 power 10 to the 10 to the power 3 flops. So like in classically, what we say floating operation per second. Here we call circuit layer operations per second, clocks instead of flops. Okay. And we support like 5,000 plus to like about 5,000 2 qubit gates. That means you entangled operations you can prepare, right? In 2026, 2025. And we are very close to the quantum advantage because some of the papers you can already see that they have demonstrated efficient utilizations of quantum computing, right? So this is the very standard state of the art currently at IBM. And recently, like the 1 month back in QDC 2025, November, so we proposed IBM Nighthawk processor with 120 qubit. Now, there is just not about qubit. You prepare certain number of qubits in the hardware, and how much control you can do on the qubit. That is very, very important. For example, this 156 qubit, this is the qubit topology. That how many qubits can talk to each other, right? So in this particular configuration, suppose qubit number 1, okay, sorry. Just let me take the ledger, maybe. So just allow me seconds. Yeah. So in this particular configuration, if you look at, So say qubit number 1, 2, 3, and so on. So there are a certain number of qubits. Now, and in some of the qubits, for example, this particular qubit can interact with this one, and this one, right? So there are some qubits which can interact with 2 qubits, and there are some qubits which can interact with 3 qubits. 2 and 3 are the interacting, like how many qubits they can talk to each other. So if you design an algorithm and that has an implementation on the hardware, and hardware should also satisfy like the criteria, right? Your algorithm should satisfy the criteria of the hardware. So this is the configurations called the heavy hex topology for the qubit configurations in the hardware. Similarly, in the one massive improvement is the NITOC processor. NITOC has 120 qubits, but that's a square topology that each qubit can talk to 4 other qubits, right? So how many entangled operations it can support, right? From 1 qubit to multiple other qubits, right? So accordingly, you can map your problem, some of the intractable problem, for example, in the 2D lattice interaction problem in physics, you can map it to the computer quite easily, right? So these are some of the advancement. Now, I already talked about 30 minutes about the basics. Now let's talk about some of the important applications, right? So this is a like a set of algorithmic problems, or how we define problems in computer science, right? The complexity classes, right? P problems, polynomial, problems solvable in polynomial time, NP complete problem, NP problem, P space. So these are the typical computational complexity classes. Where quantum sits, right? So BQP is one of the important class in quantum. Typically we work on, although there are classes like QMA hard and etc. in quantum, but BQP is very popular. So that is the bounded quantum polynomial problems, right? And this kind of problem, consider those problems. So can we find a problem which is very good, at least polynomially solvable on a quantum computer? Or can we choose a NP complete problem that can be better solvable on a, because NP complete is very, very hard problem, right? Can you solve on a quantum computer? Either it can give benefits to speed, it can give benefits to memory, etc. Right? So these are the typically computational classes, right? So mathematically, there is no proof as such that quantum computer is faster than classical. It is very hard to find, except source factorization's algorithm and Grover's algorithm. So one thing we can do is to map a particular problem on a quantum computer and work on it and demonstrate using empirical results, right? Theoretical proof. Of course, if you can do, it's a revolution. Okay, so there are so many hype. Where shall I start, right? So we need to understand only 3 things at the very fundamental level. One is called the encoding, second is evolution, and third is measurement. That's all. So encoding is for engineers. So this is a typical 3 steps in quantum computing. Encoding means you have a classical information. For physicists, they have direct representation of their problem in the like quantum level. For example, bosonic configuration, fermionic. Even it is not directly in the qubit system, they can do some transformation like the Brabicki-type transformations or the Jordan-Wigner transformations, and they can map on the qubit directly. So they have a direct definition of problem in quantum domain. But for engineers, computer science people, we have classical data like some say list of data, dictionary of data, some tuples of data, right? This is what we know. Now the first stage is how we can convert those data to quantum computer, and the technique is called quantum encoding technique, right? So quantum encoding, there are various encoding schemes. For example, the amplitude encoding, you store the classical information in the probability amplitude of the qubits, right? In the basis states. Or you can store the information in the directly basis state representation 00011011. That is called the basis encoding. Similarly, you can encode the information the angle of the qubit. You apply certain RZ ring, basically C naught provided by RZ. There are certain configuration that's called the angle encoding. There is Hamiltonian encoding. There are various encoding scheme. I'm not going in detail of various encoding scheme. This is one of the primary research area I focus on. We can discuss any other time as well. And another primary area I focus is basically this Hamiltonian simulation. where you have a matrix and that matrix may not be unitary in nature. Can I somehow convert that particular matrix to unitary to decompose into unitary basis sets like the Pauli basis, Clifford and non-Clifford basis sets that can work on a computer? So that is another step. So in engineering, we have an input, we have a system, we have an output, right? So input, I understand, okay, I can encode it, right? I can do encoding. Then what to do? I have encoded into quantum. Now I have to travel, like I need a ship to travel on the ocean, right? I need a airship to travel on the sky. So you need a unitary matrix to travel on the blogosphere, to travel on the quantum world, right? So this is your ship, like the evolution matrix, time evolution matrix, right? And this is just you can get by solving the Schrodinger equation, as simple as it is, right? So you have a evolved state. Now what to do? You need to do measurement. So there are various measurement scheme, for example. So there are lots of algorithms for evolution. You can directly, like there are in Qiskit, there are direct functions, for example, tautorizations, etc. Okay. And in measurement, you have an evolved state. Now you do, typically in Qiskit, you can do the projection operations. Those who work on density matrices, they can also try POVM kind of a positive operator valued measured kind of configurations on those state. But in simply, if you do mathematical projection of the this particular vector to zero state, so like zero inner product with psi, you can get the probability of this particular quantum state in zero vector, right, towards the zero vector. So what you get typically, you have the certain probabilities and the measurement basis set. In a particular measurement basis, say K0, what is my probability? In particular basis state 1, what is the probability? Like that, right? So these are the very basic 3 steps which are common to every algorithms, right? Almost every algorithm, and at least as soon as computation is considered, not the communication or other sensing applications, but at this computation part, these are the 3 things. Okay, so those like who already have some problem and started, and they can take advantage of our software stack from IBM. And in our software stack, we provide at various levels of flexibility, especially the Qiskit serverless. And you have some problem where part of the problem is good to solve in quantum computer, part of the problem is good to solve in classical computer. So this kind of hybrid problem, we have integration platform like heterogeneous orchestration. And okay, I'll before introducing these things, let me come to some of the applications and how we map the problem. Okay, so currently, these are some problems which are called the near-term utility problem towards advantage, right? For example, the chemistry and material simulation. In material, you know, like the number of sample space to design a new material is huge, right? The combinatorial optimizations problem. And solving a combinatorial optimization problem, if the number of like the space is very high in dimensions, as well as the number of combinations is very high. So typically a classical optimizer, for example, Cobila, these things takes huge time on classical machine. Now, can we formulate, say, for example, a quadratic optimization problem on a quantum computer, or a linear programming problem on a quantum computer? And part of the process can we solve on a quantum machine? And part of the problem can we, for example, parameter tuning, etc., we can do on a classical machine or not? So this is an active area of research currently on quantum computing. Similarly, although I mean we are not sure whether quantum computing can give some benefits to machine learning or not, I'll show some problems that some algorithm people already have tried, but I mean I am unable to answer whether it will give some advantage or not. We are not at that stage in terms of the machine learning problem. There is a number of like groups working on various numerical simulation problem. For example, computational fluid dynamics, right? Solving partial differential equations, solving linear equations, solving certain like mathematical functional mapping, etc. Right? Or a group theoretic problem. For example, if you have a special group, right, and that particular group has a particular symmetry, can that some of the problems in basically considering those kind of groups be faster on a quantum machine or not? For example, in my PhD times, I was doing for some groups like Toeble, Circulate, this kind of groups, structured groups, and I have seen that, well, if there is symmetry in certain form like diagonal, anti-diagonal, or arithmetic progress, this kind of symmetry is there. So there is way how we can design recursive algorithm faster solving on quantum machines. Okay. So these are typical areas, and you may propose some good applications. Now, typically, I divide algorithms into two ways. How, like, in terms of like how we solve the problem, how we approach the problems. One set of problem are called the fault tolerant problem, or direct, or you can say just direct circuit. Even instead of saying fault tolerant, just we can say like parameter free algorithm. And another set of algorithm is called the parametric algorithm. So if you remove this classical optimizer loop, suppose we have an encoding of the problem, you have a unitary like evolution of the problem, you have a measurement, you have an outcome. This is a direct path. Like you have a classical thing, you encode it in quantum computer, a simulated problem on our machine, you get some result, and you have done post-processing to match your parameters. So this is the direct path. Some of the problems where you don't know the exact unitary because you don't know the observable of your problem. So you have a circuit with parameters like say RZ theta is one of the parameter, theta is one of the parameter for RZ gate. So those parameter, every time you do the measurement and there is a classical loop that you tune those parameters and again you run the circuits. So this is the most of the people like work at least before 2024. There are many works, and those kind of works are called the variational algorithms. So that is the second root of problems that people initially started when the computation power of quantum computer was not good enough. So can we get advantage of both the classical part and the quantum part together? Okay. So on a quantum part, so there are two particular primitives you can have. One is like sampler and one is the estimator. These two are the primitives, and this to determines what are those tasks where quantum computers good at presently, right? So in that particular regime, there are two particular primitives. That one primitive is called the sampler. That means, okay. Somebody has some questions. So maybe I mean I am not the right person to answer this question. Professor Parthasari, they may reply later on. Okay. So in sampler, you can see like, okay, quantum circuits can generate interesting samples. I mean random samples. Okay, and can we utilize those large number of samples to some of the algorithms? For example, diagonalizations problem, matrix diagonalization problem. Because if we can diagonalize a matrix, many problems are easier to solve, right? Because it's easier to represent and efficient to solve, right? So matrix diagonalization in that particular direction, if you have a very large matrix, especially for chemistry problem, where people have molecules, bigger molecules, and bigger molecules have their like dimension is too high, like some 10 power 9, 10, or more than that. So operating on those diagonalize those matrices in order to find the ground state of a particular chemical molecule to understand various properties, or even to understand what is the dynamics of the wave functions of a particular molecular configuration, molecular Hamiltonian, is very, very difficult, right? You need to diagonalize. Diagonalization, one of the interesting applications for those problems. And quantum computer can give you, it can generate large number of samples, and you can have some some kind of algorithm that, okay, if I have a large number of samples, I can intelligently subsample it. I can take a subset of those samples, and I can project my bigger Hamiltonian into smaller Hamiltonian, and I can post-process using classical things. So this kind of mathematical operations are suitable using the sampler primitive. So I'll elaborate it later on. Another important primitive is called the estimator primitive. Suppose you have an observable age and you are interested to calculate the expectation value of this particular observable, right? So meeting is being recorded and camera. Okay. So in estimator problem, suppose you want to minimize this particular expectation value, that is your so minimizations problem. For example, this min card max flow problem, this kind of problem you can do. You can minimize certain objective functions. So this is a very basic framework for various optimizations and parameter estimation problem. Now on quantum computer, when you design algorithm, you use lots of gates, right? And from the hardware part, those gates, because they are noisy currently, have certain noise level, coherence time and all. because of the coherence time and all. So there are some noise in your result, right? How you can mitigate those results towards the actual result, right? So there are tools like the TREX, ZNE, PEC. These are various error mitigation tool. So what they do is basically, suppose, okay, one of the example I can explain. Suppose your circuit has a particular noise behavior, and you design an extrapolation technique. Okay, I fit a noise model to that particular circuit, and I increase the noise model. I increase the basically the noise intensity of that particular circuit to understand the noise behavior, and slowly that parameter lambda of noise intensity, I make it go towards 0 of the extrapolation value, such that I can get the highly mitigated version of the actual circuit. So that is a GNE, or the zero noise extrapolation technique. So these are the good techniques before error corrections to get useful results from the quantum computer. Now let's compare, like if you have an image processing problem, for example, how to map this problem or how to think this problem in terms of quantum computing algorithm. So this is how we can think of, right? So what typically we do in image processing, you have certain image, right, labeled image, and in a for example classification problem, you try to understand, okay, what image it is from a new example, right? Unknown particular example, right? So you have a typical number of say for example, if you solve this problem using a convolutional neural network, right? So you have an image, right? Image is a matrix, right? So you can look at the pixel values or some other attributes, right? And what you typically do, you do some sort of filtering. For example, the convolution operations you can do basically dimensional reduction, whatever you want to do, right? Then you basically, after the filtering, what you do, basically, you do some decision making, right? So even at the filtering stage, you can do some basically activation function, multiplication, etc., right? So similarly, on the quantum side, so this is not an equivalent path, but just I'm showing the similarity, those just who are coming from the classical background directly. So you have a classical data X, so you prepare an encoded version KTX. So in Qiskit, you write QC, like quantum computer circuit at QC, QC.initialize, that particular functions can help you encoding a particular classical informations in the quantum state. So those who are interested, you can just write, okay, how to encode classical data on a quantum computer, and it will give you all the information. Those who are interested in the noisy versions of the data, they can also take advantage of the density matrix approach. So I'm skipping the density matrix part. The next stage is the filtering part. Like you have a classically, for example, you are doing the Fourier transformation, or you are doing the convolutional transformation, or certain hidden layer information, how you are converting your original informations to a basically changed vector or evolved vector, right? Modified vector Y, right? So here you need to prepare the unitary versions of that. That's why here it is written U1, 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 V1. These are various unitary equivalent operations of the classical approaches, right? So this is the first level. This is the after first hidden layer. This is the second lines of mathematical operations, right? So this is not a straightforward fitting. Okay, you need to design the algorithms, how you can convert those things. So even like designing a filtering algorithm is also like a huge task. So I proposed, like from our group, we proposed an low pass filtering algorithm in quantum, and that was there in the Nature. So I'll show. Okay, I already have given the link here. Okay. Then what we do after the transformation, so we typically either can take binary decision, okay, what is the level of the information, or basically continuous informations like what is the temperature of a day, etc., right? These kind of applications. Okay. Okay, I'm skipping this source algorithm, etc., because I did not cover the information theoretic aspects. So this is just like source algorithm. There are two parts. One is the quantum Fourier transform, or the quantum phase estimations you can consider, and the second part is the modular arithmetic. So I'm skipping this part. I'll share a link. Those who are interested can see my lectures already there. Okay. We were talking about problems, right? So what sorts of problems are interesting, or so we discussed about simulation problem, like chemical molecule simulations, optimization problem, like there are various optimization problem everywhere, right? So one of the interesting optimization problem we'll look at, and one quantum machine learning stuff we can discuss. Okay, so this is one interesting work around discovery of the finding mRNA secondary structure using a quantum computer. So you can take a snapshot. Maybe this is a work between IBM Research and Moderna, and this work is implemented on 80 qubit to find the mRNA sequence based on the quantum optimizations algorithm. Okay, so variational algorithm, I'm just keeping, okay, so some I have many like 94 slides. I cannot cover all this in time, but some of the interesting problem I'll cover. For example, the combinatorial optimization problem, max. So suppose you have an objective function cx, it can be your x transform ax plus bx plus c, can be a quadratic problem, for example, right? And this kind of problem we typically look at in network optimizations and many places, right? So to maximize a particular function or minimize a particular functions, right? And for example, the knapsack problem, right? X is the selection of items to include in the knapsack, right? Packaging, and Cx is the total value of the items, right? Vehicle routing problem, X is the routes for a fleet of vehicles, and Cx is the total distance traveled by all vehicles. Job scheduling problem, it can be job can be scheduled on machines, and total number of jobs completed is Cx, right? Something like that. So this is like the main contribution in an optimization problem is not the algorithm. If you can propose an algorithm, that's a great thing, but at least how you map the problem, how you mathematically define the problem, there is the contribution, right? So this is how you define the CX, right? In a particular regime, and then basically you are minimizing or maximizing this thing. So okay, there is some approximate on these things. So this ratio I'm just skipping because there is an optimal ratio, etc. But at least okay. So max cut problem, for example, this graph coloring problem. Think of a graph whose nodes you have the color using green and yellow, and age can be u comma v set to be cut if the color of u is not equals to the color of v, right? The max cut problem. And consider an assignment of color, like x is a bit string of x1, x2, xn. So I'm not going detail to the algorithm, we can discuss later, but yeah, I mean, you define the cx like this, like xu plus xv and minus 2xu 2xv. This is the like the graph coloring problem, and we just need to solve it using a max cut. And okay, so this problem you can basically convert it to the quantum domain problem using an encoding called a QB encoding, quantum basically binary optimizations problem in the binary bit string wise representations and solving it. And basically converting those variable into G operator. G is the mathematical Pauli G operator. Okay, so Cx, this particular objective is converted to C of Z, where G is the Pauli G operator. So there are some steps. Okay, this is not just I'm just not going hurry, but these are certain steps. So how you convert your actual objective to the objective functions, where this objective is represented either as a Hamiltonian, right? So most of the cases, it's you need to write it as a Hamiltonian, and that particular Hamiltonian has to be written or decomposed into the Pauli bit string or the clipboard or non-clipboard bit string, and then basically we need to optimize this problem. So the earlier I already have shown the estimator primitive, right? So you have, when you already have an objective functions, right? So for example, if you work on the G operator, Pauli G operator, and one interesting property of the G operator is that, so definition of G operator is 1, 0, 0, minus 1, and G applied on 0 operator, 0 vector is 0 vector, and G applied on the 1 vector is minus 1 vector. That means 0 and 1, these are the eigenvector of the mathematical operator Pauli Z, okay, Z operator. So that means if you measure these things, you'll be getting +1, and if you measure these things, you'll be getting -1, right? So you just need to count how many times I'm getting +1, how many times I'm getting the -1, right, out of the measurement, right? And accordingly, we can solve the QB problem. And so there are, like, how we solve this problem, there are certain philosophies. One of them is the adiabatic algorithm, QAA. Suppose you don't know the exact solution, so you assume, okay, there is an like gaze of solution, and then we slowly approach towards the final solution. So slowly and slowly, like the thermal process in the adiabatic process. And there is another route, or this is like part of the route, like the QAOA, quantum approximate optimization algorithm. So where basically we use the tautorization of the QA approach. So this one, adiabatic approach. So here your unitary operator, you don't know the exact unitary operator. So you take the parameterized versions of the operator that I have an operator, unitary operator, which is parameterized with gamma and beta. Right? Okay, and can I train this gamma and beta such that the overall objective is satisfied? Like I reach to a point very close to the HP point, right? The actual desired Hamiltonian point, right? So there is a threshold and you need to like check the threshold. Like this operator times the initial state, the final state should be as close as possible to the desired thing. So this is a philosophy, and of course, like you need to train with a classical optimizer for the gamma and beta, and that is followed to get like the optimization algorithm Q and Y. This is a hybrid algorithm. So, okay, these are the steps I'm skipping. Just we need to check the convergence and all. And if you have constant, so how we solve it? Like basically you prepare a Lagrangian and basically directly by instead of like solving individually the objective and the constant, you can define a Lagrangian and directly work on the Lagrangian objective functions to get the minima or maxima, right? Putting the constant into the objective like that. So these are the detailed steps I'm skipping. So just because it's a 1 hour 30 minutes, I'm just giving summary of some of the things. Okay. So in general, what we are doing, we are creating a random, basically initial parameters, gamma and beta, I mean circuits with these parameters, right? And we prepare an initial state G as a ground state of the Hamiltonian, because this is the state we don't know, like some initial state we take as a ground state, right? And then basically our objective is to calculate this expectation, like given the Hamiltonian and the state parameters gamma and beta, the expectation value of that, right? So this is the route, like how we design the circuit, which is the parameterized versions of the quantum gates with parameters beta, or you can take, like this is the beta versions, you can take add the gamma as well, and then you optimize beta and gamma, and finally you can get an optimal versions of the circuit. So this is just a one application side of quantum computing algorithms. So even people are using QAOA for portfolio optimization in quantum finance, in network optimizations, many places. Another interesting application is quantum-driven diagonalization. So that particular work, there are number of authors, and including IBM, RIKEN, University of Colorado Boulder, and I am also part of, like I'm a visiting scientist at RIKEN, Japan. So I was there last year, and again in March I'll be visiting RIKEN. So there are some interesting work going on around the diagonalizations problem, and so what typically these things are interesting, I'll come. So I'm skipping some of the basic stuff. Okay, so this is the important problem. Suppose you have a like a problem, like molecular simulation problem, where you need to diagonalize in order to understand, okay, what is the ground state of a particular material, of a particular chemical component, right? Or even you want to understand, okay, if I have a potential energy curve, okay, and what is the minimum energy required to dissociate a particular molecule, right, into smaller component, right? So those are the questions related to the chemical thermodynamics, right? And here, these are very difficult questions to answer on a classical machine because of the computational limitations, especially if the number of orbitals are high, right? So, for example, if you take Fe4S4 molecule, right, the iron sulfur cluster, so the problem size is very high, and if you solve on a classical machine, it takes very long time. So what we did, we have a so partly we'll be solving on the quantum machine, and partly we'll be solving in the classical machine. You have a bigger Hamiltonian. Can you design certain projector PS, and like the projector will basically the bigger Hamiltonian is H, and those using those projector, basically I can basically get a subspace versions of the Hamiltonian, which is possibly reduced in dimension from the original Hamiltonian. And how to create this basically projector is basically depending on how you create interesting samples from the quantum computer. And those samples, how you actually, out of those many samples, how you can get a subsamples, interesting subsamples, which contribute towards the design of the eigenvectors of a but bigger Hamiltonian, right? So if you find some interesting bit string X after the configuration recovery from the samples as the outer product of those bit string as your projector, then you can basically get a reduced dimensional Hamiltonian. Once you have a reduced dimensional Hamiltonian, then you can do the classical eigenvalue decomposition and get those eigenvalue of the lower energy states, right? So this is an interesting, very interesting work known as the SQD algorithm, sample-based quantum diagonalization. And there are many interesting work, and two extension of the works we are also doing with IIT Bombay and SN Bose. I'll show, probably if the papers are there, I'll show in the slides. So those are applications and extension of SQD to one interesting direction is to study 1D and 2D lattice for like magnetic phase correlation in physics, and another is with quantum chemistry department at IIT Bombay towards simulating large number of molecules and preparing those initial state, how intelligently we can prepare them. So we have an archive paper here. So there are some generative AI based machine learning techniques are used to basically generate these interesting initial wave functions, right? So there is like how we like, this is a philosophy how actually this lower dimensional things work. For example, 4x4 Hamiltonian, you can see, right? This is a matrix with 16 element, right? Can you design something interesting to for 2x2 matrix? Then there will be huge computational memory advantage, right? And suppose you just map these problems. Suppose you start with 0, 0 qubit to 1, 1 qubit, how you map the problem. So, and the eigenvector suppose is A, 0, 0, B, right? A belongs to the qubit 0, 0, and this B belongs to the qubit 1, 1, and H psi equals to lambda psi is the equations, right? So, okay, some of the slide I wish to acknowledge my colleague, Dr. Ritojit and Dr. Like Miss Janani. They are amazing people in our group. So some of the slides I took from them. So I want to acknowledge them here. Okay, so H psi equals to lambda psi, if you just write these big Hamiltonian equations like this, and just you break these linear equations into smaller parts, and you can see this, these two components are contributing nothing, right? So in this particular second and third equations are contributing nothing, so you can just eliminate them. And you can write the reduced versions of the equations like A H00 plus B H03. So you can see just because of this interesting like this particular eigenvector, you can reduce this Hamiltonian into a smaller Hamiltonian, H00, H03, H30, H33, the much reduced versions from 4x4 matrix to 2x2 and AB. Now the question is, how can I get this eigenvector is another interesting research questions, right? So this is like quantum circuit can help you to identify with interesting ways to these eigenvectors, but not 4x4. These are very large dimensional vectors, right? Very, very large dimensional vector. So because typically this is order of n to the power 3 is the complexity, right? And if your dimension is, say, for example, 10 to the power, say, or 2 to the power, in fact, say 10, and 2 to the power 10 times whole to the power 3, 2 to the power 30 becomes your computational complexity, like number of operations, typically, ideally the upper bound, right? So that's how hard it is, right? So it's a very computationally complex problem. So can you break down the problem, and possibly a part of the problem can you do faster on a quantum machine, right? So there is not a direct fitting like, yeah, you call a CNN algorithm, fit to some problem and get an answer. You put a GAN algorithm on some images, get an answer. This is not at that stage quantum, right? We need to work hard, even for simple problems, whether at all we are getting some advantage or not. But of course, this is the time to do large scale problems on quantum machines, right? It is not like just increasing accuracy of machine learning problem by 1%, but it is targeting those problems which are difficult to solve on classical machines, Can you solve on a quantum machine or not? So these ground state like problem finding in quantum chemistry, because I'm just skipping this part. Maybe audience might not be mostly from not from chemistry, so I'm skipping this. But possibly SQD can also be equally useful for example, MIMO communications. Many places you have large scale matrices, right? You need to diagonalize, right? How can you take advantage of quantum machines for some of your channel design, equalizer design, right? Your precoder design, there are many problems, and you can think of how quantum computing can be beneficial for those problems. Even the QAOA algorithm for network optimizations, right? Control problem, filtering problem, right? So you can look for, so these are very common in engineering. Okay. This is the details of SQD algorithm. I'm skipping, not going in the details, how it works and all, configuration, recovery, etc. I'll take 5 to 10 minutes to cover some of the interesting stuff in machine learning, maybe. Just skipping these things. So this is a part of the many body physics simulation problem. And one of the interesting stuff like IBM has been doing with LHC experiment, Large Hadron Collider with CERN, Day6 in Germany, right? So these are some of the interesting stuff, and this is one small piece of works from that particular group. Those who are interested in the diagonalizations problem, they can use IBM add-on Qiskit, this particular module. So you can do pip install this particular module, and you can see like how to use this particular module to your diagonalizations problem. So this is just you don't need to start at like from the scratch, but IBM provides you tutorials to start, right? And then you can think how it can be helpful to your problem. So this is the paper. I think the main paper came in, I think, Science Advanced Journal, which is a very high impact journal, this particular work. Now let's talk about this quantum machine learning stuff. Okay, is there a quantum algorithm that learns data patterns better than a classical model? We don't know. Okay, so whether it is better or not, that's a futuristic question. But at least, okay, can a quantum computer solve a machine learning problem, and up to what accuracy? So that's an interesting question. Or what sort of problem that classical computer cannot provide that much good accuracy because of the data complexity, nonlinearity, or data scarcity, or dimensional problem, or training problem, or overfitting problem, or bias problem. In those very difficult situation of classical machine learning, can quantum help us or not? These are interesting questions. Okay. So as I was saying, there's a various encoding technique for the problem. For example, basis encoding, amplitude encoding, angle encoding, dense encoding, phase encoding. These are various, how you can map your classical data on a quantum computer. But I mean, it will take some time to understand which technique is good for your problem. But probably you should come up with your own like method, or you need to find out which method is good for your problem. There are various feature embedding method in quantum. For example, efficient SU2, G feature map, GG feature map, Pauli feature map. These are available in Qiskit to use, right? And what we need to look at when you design an algorithm, we need to understand, okay, how many qubits we require to solve the problem. This is not just qubit, but what is the depth of the circuit? That means how many quantum operation I need to do on those qubits to get the probability distribution favorable for your solution, right? These are interesting questions. Say now, suppose this is a typical, these are some of the applications. This is for example, the classification problem, right? You have basically a data, and can you find a hyperplane that you can basically possibly distinguish these two particular class or classify these two classes, right? And with the good confidence, like confidence as well as the accuracy, right? So this is a classification task. You can have prediction tasks, like you have some data pattern, say for example, temperature, etc. Weather prediction, for example. So if I give you some 100 data points, can you predict some of the future points, stock market data, time series data, etc. Right? So these are two typical examples of machine learning problem. And this is a typical chart, like quantum data, quantum method, classical data, quantum method. So this is very like popular chart I just put here. Okay, I don't know like how I should explain this in terms of this particular example, but okay. But at least, okay, let's understand mathematically how, like what does it mean. So suppose you have a, like this particular typical example of support vector machine problem, right? You have two class of data points, right? Which are basically jumbled up data point. If you see this part, and you either design, either you convert this problem to a another domain, where either you augmented that problem to such a trick to a augmented domain that you can find a hyperplane, and above which you have one particular set of data, and below which you have another set of data, right? And that particular hyperplane finding is the objective, right? So how to do that basically? So towards the one set of cluster after the conversion. So how do we convert this original domain data to another domain is called the kernel trick, and the functions we get are called kernel functions. In mathematics, they are kernel matrices, right? So suppose, for example, you have the featured data x1, x2, and after the featured data, like after conversion, suppose you get phi of x bar, that's x1, x2, and x1, x2, right? This is how, I mean, there are ways, right, how to do that. So how to solve this problem? There are primal solution, dual solution, KKT condition. I'm not going in details. So the philosophy is that in one part of the data set, you find some of the vector points called the support vectors. In the another set of data points, you get another set of support vectors, right? And can you design a particular affine functions or a hyperplane, right? Which are which has equal distance from these two support vectors, right? And it should be designed as such that there is minimum number of data points from class 2 to class 1 and vice versa, right? That means minimum mismatch or the error, right? So that is the philosophy of SVM, right? Now, of course, this problem conversion from original domain to quantum domain, there is something called the kernel, which convert the original domain problem to the modified domain, right? Like the domain where you have the modified data or the transform data, right? Mathematical transformation you are doing. So that is what we call the kernel. And this is a kernel matrix, works with the basically inner product of the feature vector with the kernel functions k, right? And equivalently, can you design some algorithm on quantum, right? So can you design this thing? So what typically we do, you are doing the inner product of the feature vector, right? And in quantum, you have a circuit to do inner product. So that is called the swap test circuits. So two ways you can do. Either you can go with the inner product conversions, like the converting the feature to quantum domain and doing the inner product, like the kernel itself can be a quantum kernel. And after conversion, you can do classical post processing. This is one way. Another way is that you have a kernel, and can you find an equivalent unitary matrix for this particular kernel matrix? And if you have input data already in like quantum state, and you apply this particular unitary matrix equivalent of the kernel matrix, and you can manipulate the probability such that one class of a problem goes to one set of basis vectors, another set of data point goes to another set of basis vectors, and you can resolve them, right? So this is a important algorithm. This is an important, and it is called the quantum kernel method for SVM or quantum SVM. And there is a detailed tutorial on quantum kernel learning. So on internet, like from IBM tutorial site, you can look at like QS quantum SVM in Qiskit. So you can see the implementation, detailed mathematics, Qiskit implementation. So these are some of the steps already I just discussed, and you can implement on your machine. Okay, so these are like, we have some papers from IBM research team, and I'm honored, fortunate to be part of those. So these are some of the papers from our group published in Nature portfolio. And these are some other interesting stuff, an interesting paper from our IBM TJ Watson Research Lab. This is one paper, white paper, or currently there are some good applications also in pharmaceutical applications. So one of the paper came recently, I think, from this biomedical domain in Nature Communication. Recently, I forgot to put the link here. And this is an interesting application of quantum machine learning in clinical setting, like clinical optimizations for efficient, like patient, like efficient delivery of medicine to the patient. This is one work we proposed towards the potential energy simulations, and we proposed a new encoding scheme called the polynomial encoding scheme to get optimized quantum gate, like the gate complexity optimization. So I'm not going how it works and all, skipping it. These are certain mathematical theorems, proofs, etc. These are some applications in cell-centric therapeutics. Okay, can quantum computer help us to identify potential drugs for a given disease or given problem, right? How quantum like algorithms can help us. So in inline work is to identify a particular candidate protein, right? So whether given a situation, a particular protein will form or a disease will occur due to misfolding, right? So there are certain interesting works, and this is like this is one of the interesting paper on the tetrahedral lattice polymer model of the protein, published in 2021 Nature NPJ Quantum, as well as some other interesting papers are also published in 2025. And there is one interesting works from our group, Dr. Kalyan and IIT Madras is doing around this cubo encoding of large, like at least proteins beyond 65 qubit scale, right? I mean, at the utility applications thing. This is an interesting work in genome sequencing problem. So given various the segments of sequence, right? The adenine, guanine, uracil, thymine. So these are the DNA, the nucleic acids. The nitrogen. So in the DNA, like deoxyribonucleic acid, so there are these bases, right? Like the ATCGU, right? And U is typically for the RNA. Now, given this fragmented pattern, can you sequence them properly to identify a particular patterns of sequence, which can tell us, okay, this particular, when we get infected from some particular virus or bacteria, certain things, okay, given from their fragmented DNAs or fragmented these nitrogen bases, we can say, okay, we can form a particular sequence and say, okay, this is the particular bacteria or virus it attacks, right? So these are this sequence formation is basically a traveling salesman's problem, and it's a NP complete problem, and so there are some of the interesting approaches people already proposed, and this is one example paper. Yeah, I mean, I can share some of the slides, or you can take screenshot. The entire PPT I may not share due to some complications, but yeah, of course, some paper links I should share. That is possible. You can also take screenshots for the papers. Just typing the title will give the paper, or I can find and provide. This is, for example, in this paper I have already cited 4 interesting citations, right? In quantum computing applied on image processing problems, right? So there are papers like breast cancer classifications, how quantum is good or bad, okay? So new RIPS published in new RIPS, one in the archive paper is there, as well as this medical image analysis journal paper. So this is another interesting paper from like IBM as well as other international groups, okay? So you can see like here the images are encoded in graphs, and then people use the graph neural network, okay, and then convert it into 2 ways. One is the MLP based basically conversions technique, multi-layer perceptron. Another is encoder versions. Encoder versions basically it converts basically this kind of data into the encoded quantum states, and people applied the variational quantum classifier on top of it using certain quantum answers, and based on the output, people predicted that, okay, for data sets where the data is scarce, okay, their quantum computing might have some accuracy compared or competitive with the classical counterpart. This is one interesting work that we have done on filtering. Say, for example, ECG signals, and how can I filter ECG signal using a quantum smoothing filter? So this is like the matrix inversion based filter, like the notch filter we have designed on the quantum regime, and this has pretty much good result. You can see in this particular plot if. So we compared it with classical empirical decomposition MD techniques, which are extensively used in ECG signal, as well as the discrete wavelet transform DWT. And our work is pretty much good. It does not have energy loss. It does not have aliasing effect, and it has a good good advantage in terms of the runtime complexity as compared to the other methods, at least theoretically. So, okay, SQD already I talked. This slide is repeated. I can skip them. And these two works you may look at. These are the two very recent work. This is from IIT Bombay papers, led by Professor Rahul Moitro. So we have been collaborating with this group. So they have the diagonalizations problem for bigger size molecules like the nitrogen, water, as well as right now they are doing much bigger size molecules. So how they're preparing how they are taking advantage of AI to prepare interesting quantum states which can contribute towards the computing eigenvalues, right? On top of the diagonalizations approach proposed by the SQD paper, right? So this is a work that is there in archive. This is the link, and also I think this is submitted to Nature Communication last week. And this is a similar work in the in physics simulations to study the quantum phase correlations. I have been doing with like Anutosh, Shayon, Ritojit. So these are the people like under guidance of Professor Manoranjan Kumar. They're working on quantum physics simulation using the quantum computation framework. So to understand various quantum phase correlations in magnetic materials and various other materials. And so here also you can see, okay, there like algorithm like basis adaptation algorithm is proposed, which has pretty much a good result in terms of the complexity reduction for many body physics simulation problem with SN Bose Center for Basic Sciences. Well, I think I have done in summary. So we are doing interesting stuff, and we ask people to work on quantum computing with confidence. So there are lots of learning materials on IBM sites and on internet. And we typically ask scholars, students to at least help us on quantum compilers, transpiler design, runtime hybrid workflows, applications development. So take advantage of IBM quantum hardware, the software tools, as well as learning resources, and let's do some utility applications jointly towards quantum advantage. So this is a book we have recently written, KATE 0 and KATE 1. And I think there is a number of good books, and this one is for all, like without any background. Those are very beginners. So this is a gentle introduction to that. So thank you all, and please feel free to ask many questions. I'm stopping here now.
Thank you, Dr. Mustafizur Rahman, for your excellent talk. There's one question in the chat box. Is there any platform like Collab which is free to work with quantum computing?
So Qiskit is totally free. You don't need to pay anything. So Qiskit, you just need install in any Python environment. So Colab is right an interface. You can either work on Colab, or you can work on Anaconda, Jupyter, whatever Python, like Spider, for example. I'm writing the names, or even VS Code, right? So wherever you prefer, you please download any Python environment and then do pip install Qiskit, right? And I'm just sharing one link that probably, okay, just allow me maybe 30 seconds. So IBM Quantum Learning Platform. So there are lots of resources. So this one link itself sufficient. So you can go and all the learning resources, Qiskit examples, everything is there. And okay, Qiskit. Another link maybe I can provide. So I have provided these two links. Please just take these two links, and there are all the details, installation guides, everything is given. Okay. And even after that, if you face any problem, I am available on LinkedIn. You can drop me a message. I'll try to answer one by one. Any other questions, sir? Okay,
Explain about
QC,
yeah.
QC is like data is quantum, method is classical. Data is classical, method is quantum. QQ is data is quantum, and also method is quantum. This is not our diagram. This is a very popular diagram that is visible everywhere on the internet. I just put it. But you don't need to remember anything. You have a classical input. You need an encoding to go to quantum. You propose an algorithm or use an algorithm to solve your problem. Then you have an like evolved state, and you need to do quantum measurement, right? Once you do the quantum measurement, you get the classical data back. But those classical data are probability amplitudes. You don't, I mean, it doesn't make any sense with just probability amplitude or probability mass functions PMF. So that particular probability associated with the particular computational basis states, those are the important like what these probabilities signify to corresponding a particular computational basis state. That phenomena you have to convert or post process to your actual parameter set. So that is the flow, how you solve your problem, right? Okay. Okay, so I'll be sharing the papers link and some of the slides. Maybe I'll be sharing with Professor Sudarshan sir. Any insight or particular challenges associated with quantum ML which could not be solved with classical ML? Okay, I am keeping this question open. You can search on internet. There are lots of problem open. But I mean, guaranteeing that you have an algorithm which can solve better on quantum is not done yet. People propose certain things competitive with classical things, and people are working on it. And this is an active area of research. So many things are open. Yeah.
Thanks a lot, Dr. Rahman, for joining. It was an excellent talk. Thank you for your time. It was very nice of you, and it was such a fitting finale for our FDP. Thanks a lot.
Thank you so much.
So participants, I have shared the feedback link for both the sessions and the attendance link in the chat box. You can just scroll the top and you can see it. And you can give your feedback in the ATAL portal also. After today's exam, you can give the feedback in the ATAL portal also. Maybe on Tuesday or Wednesday, I'll be uploading the attendance details and the marks in the portal, ATAL portal. Maybe after that, you'll be able to download your certificate. And I have sent one PDF also in the WhatsApp group, reflective journal PDF. You can take a couple of days. At least some of you can fill that and email it back to me. Okay. So now we'll just go ahead with the valedictory session formally. I would like to thank AICTE ATAL for sponsoring this FDP. I would like to thank all the speakers who gave us some excellent talks over this week. I hope all of us learned a lot. I would like to thank my scholars who helped me in conducting this. I would like to thank my co-coordinator, Dr. Maheshwaran. I'd like to thank my department, our HOD, our Dean RNC, and our director, ma'am, for giving us the permissions to organize this. And finally, I would like to thank all the participants. It was very nice doing this with you. You asked lots of very interesting questions. I got some very good feedback from the the people who gave the talks, that the questions were very nice. Thanks to all of you. Thanks to one and all. Now the AICTE ATAL wants some video feedback from the participants. So some of you can just start your video and unmute yourself and give the video feedback. Thank you.